Have you ever looked up at the night sky and felt a strange tug of curiosity, wondering if there's more to the universe than what meets the eye? The cosmos is full of secrets, and some of them defy everything we think we know. Take this for example, galaxies, those vast islands of stars, are moving in ways that shouldn't be possible. The math says they're being pulled by something invisible, a force we can't see, touch, or even fully understand. It's as if the universe is whispering to us, hinting at hidden rules that shape reality itself. This isn't just about distant galaxies, though. These mysteries reach into every corner of existence, from the way particles communicate across impossible distances to the unseen energy stretching space itself apart. Scientists call them dark matter, dark energy, quantum entanglement, names that sound like science fiction, but they're very real. And they're proof that the universe is far stranger, far more intricate than we ever imagined. Behind the scenes, these forces are the architects of everything. The reason stars ignite, the reason time flows forward, even the reason you're here at all. So what if I told you there's not just one or two of these hidden forces, but dozens? Today, we're pulling back the curtain on 30 of the most astonishing cosmic phenomena, the silent puppeteers behind reality as we know it. Some will bend your mind, others might shake your understanding of physics, but all of them will leave you seeing the universe in a whole new light. This isn't just a journey through space and time, it's a dive into the very fabric of existence. Ready to uncover what's really out there? Let's begin. Picture the universe not as a static stage, but as an elastic sheet, stretching wider every second, faster and faster, as if some unseen hand is pulling at the fabric of space itself. This isn't science fiction, it's the reality we live in thanks to dark energy. In the late 1990s, astronomers made a discovery that shattered our understanding of the cosmos. Distant supernovae were dimmer than they should have been, meaning the universe wasn't just expanding, it was accelerating. The culprit, a mysterious force that makes up a staggering 68% of everything in existence, yet we can't see it, detect it directly, or even explain what it truly is. Think of gravity as the glue that holds galaxies together, the force that should be slowing everything down over time, but dark energy does the opposite. It's like blowing air into a balloon with no end, an anti-gravity effect that pushes space apart faster than gravity can pull it back. Scientists describe it using the lambda CDM model, the closest thing we have to a cosmic rulebook, where dark energy is represented by lambda, a symbol for the unknown. Yet even this model leaves gaping questions. Why does dark energy behave this way? Is it a property of space itself, or something far stranger, like a field permeating the universe? Here's where it gets eerie. If dark energy's strength changes over time, it could reshape reality's fate. Too weak, and gravity might eventually reverse the expansion, collapsing everything in a big crunch. Too strong, and space could rip apart atom by atom in a big rip. For now, it's holding steady, but that itself is a puzzle. The universe's acceleration should dilute dark energy's influence, yet it seems constant, as if fine-tuned by some cosmic architect. And perhaps the most humbling thought, we only discovered dark energy because we happened to look at the right moment in cosmic history. Billions of years from now, the evidence could vanish as galaxies accelerate beyond our view, leaving future civilizations with no clue this force ever existed. It's a reminder, the universe isn't just keeping secrets, it's erasing them. While dark energy stretches the cosmos apart, another unseen force works in the shadows, holding it all together: dark matter. Imagine a spiderweb, invisible but strong enough to catch entire galaxies in its grip. That's essentially what dark matter does, an invisible scaffold woven through the universe, its gravity bending light, warping space, and keeping galaxies from flying apart. We can't see it, touch it, or even detect it directly, yet without it, the night sky would look completely different. The first clues emerged in the 1930s when astronomer Fritz Zwicky noticed something bizarre about the Coma galaxy cluster. The visible stars simply didn't have enough mass to explain how fast the galaxies were moving. Something unseen, something making up most of the cluster's weight, was holding it together. Decades later, Vera Rubin found the same anomaly in spiral galaxies. Stars at the edges orbited just as fast as those near the center, defying Newton's laws unless an invisible mass was anchoring them. The verdict: dark matter outweighs ordinary matter 5-1. One of the most striking proofs came from the Bullet Cluster, a cosmic collision where two galaxy clusters smashed through each other. The visible gas slowed down, heated up, and got stuck in the middle, but something else kept racing ahead. By mapping the gravitational lensing effects, scientists realized most of the mass had sailed right through the collision unaffected. That could only mean one thing: dark matter doesn't interact with light or ordinary matter except through gravity. So what is it made of? The leading candidates are WIMP, weakly interacting massive particles, hypothetical entities that barely notice the rest of the universe except through their sheer gravitational heft. Experiments like the Large Underground Xenon Detector hunt for rare collisions between dark matter and ordinary atoms, buried deep underground to shield from cosmic noise. Others scan the skies for gamma rays, the faint fingerprints of dark matter particles annihilating each other in space. Yet the mystery deepens. Some galaxies seem to have less dark matter than they should, while others defy predictions entirely. Alternative theories suggest we might need to rewrite gravity itself, though the evidence still favors an invisible cosmic glue. One thing's certain: dark matter isn't just a placeholder in our equations. It's the reason galaxies exist, the reason planets formed, and perhaps even the reason life had a chance to emerge. Without it, the universe would be a sea of scattered stars, dark, lonely, and unrecognizable. Now imagine a universe so restless that even empty space isn't truly empty, where particles flicker in and out of existence like cosmic fireflies, vanishing almost as quickly as they appear. This is the bizarre realm of quantum fluctuations, where the rules of classical physics break down and the vacuum of space itself crackles with energy. These microscopic disturbances might seem insignificant, but they hold the key to some of the universe's grandest structures. Without them, galaxies might never have formed, and reality as we know it would look entirely different. At the heart of this phenomenon lies Heisenberg's uncertainty principle, which tells us that on the smallest scales, space is never perfectly still. Even in a complete vacuum, energy isn't constant, it jitters unpredictably, borrowing tiny amounts from the universe to spawn particle-antiparticle pairs. These virtual particles live for mere fractions of a second before annihilating each other, returning the borrowed energy like a fleeting cosmic debt. But their brief existence has profound consequences. During the universe's earliest moments, quantum fluctuations were stretched by rapid inflation, imprinting tiny density variations in the fabric of space-time. Over billions of years, those microscopic ripples became the seeds for galaxies, clusters, and the vast cosmic web we see today. The proof lies in the cosmic microwave background, the afterglow of the Big Bang. Satellite missions like Planck have mapped its faint irregularities, revealing patterns that match predictions from quantum theory almost perfectly, those faint temperature variations. They're literally the amplified fingerprints of quantum noise from the dawn of time. Even more mind-bending is the idea that virtual particles might shape the universe on larger scales. The Casimir effect shows how these fluctuations can create measurable forces. Place two metal plates extremely close together in a vacuum, and the sheer abundance of virtual particles outside them pushes the plates inward with detectable pressure. But here's where it gets even stranger. Some theories suggest quantum fluctuations could explain dark energy's mysterious behavior, that the vacuum's restless energy might be driving cosmic acceleration. Others propose these fluctuations could spawn entirely new universes, bubbling up like foam in an endless multiverse. Yet for all their power, quantum fluctuations remain elusive. They're the universe's quietest architects, sculpting reality from the shadows, one ephemeral particle at a time. The next time you gaze at the stars, remember, the vast galaxies above owe their existence to the tiniest tremors in the void. There's a moment in the universe's infancy so bizarre it defies intuition, a fraction of a second when space itself erupted, stretching faster than the speed of light. This wasn't just expansion, it was cosmic inflation, a turbocharged burst that smoothed the cosmos like ironing out wrinkles in a sheet. In the late 1970s, physicist Alan Guth stumbled onto this idea while wrestling with a paradox. Why does the universe look so uniform? Distant regions billions of light-years apart share the same temperature, as if they'd once been neighbors, but without inflation, they'd never have had time to exchange heat. His solution, a fleeting epoch, just a sliver of time after the Big Bang, when the universe ballooned by a factor of 10 to the power of 26, a decimal point followed by 25 zeros and then a 1, in less than a trillionth of a second. The mechanics are stranger still. Inflation wasn't driven by matter or radiation, but by a mysterious field called the inflaton, a sort of cosmic spring loaded with potential energy. As this field decayed, it released energy that reheated the universe, filling it with the hot plasma of the Big Bang's afterglow. The theory didn't just solve the uniformity problem. It explained why the cosmos isn't riddled with magnetic monopoles, exotic particles predicted by grand unified theories but never observed. Inflation would have diluted them to near non-existence, sweeping them to the edges of reality like cosmic dust. Proof arrived in the cosmic microwave background, the universe's baby picture. Satellites like Decode and Planck mapped its temperature with exquisite precision, finding variations no larger than 1 part in 100,000, exactly the subtle wrinkles inflation's quantum fluctuations would leave behind. Even the pattern of these ripples matches predictions, slightly more energy in large-scale waves than small ones, a fingerprint of space's exponential stretching. But inflation's legacy goes deeper. Those quantum ripples, magnified by inflation, became the scaffolding for galaxies. Without them, gravity would have had nothing to amplify, leaving the universe forever smooth and dark. And perhaps most hauntingly, inflation suggests our cosmos might be one bubble in an endless froth of universes, each with its own laws of physics, a multiverse where the constants we take for granted, like the strength of gravity or the mass of an electron, are mere accidents of our bubble's birth. Yet mysteries linger. What triggered inflation? What exactly was the inflaton? Some theories propose it's tied to dark energy, or even that inflation never truly ended, that pockets of space are still inflating today, spawning new universes beyond our horizon. One thing's certain, this fleeting moment, over in less than the blink of an eye, set the stage for everything, the stars, the planets, and the very atoms in your body. The universe didn't just grow, it exploded into being, leaving echoes of its thunderous birth in the silence of the night sky. Einstein once called it spooky action at a distance, a phenomenon so unsettling it made him question the very foundations of quantum mechanics. Picture two particles born from the same quantum event, forever linked no matter how far apart they drift. Change the spin of one, and the other instantly flips too, as if they're sharing a hidden whisper faster than light itself. This isn't magic, it's quantum entanglement, a baffling reality that defies our classical intuition about how the universe should work. The story begins in 1935, when Einstein, along with physicists Podolsky and Rosen, devised a thought experiment to expose what they saw as quantum theory's absurdity. Known as the EPR paradox, it argued that if quantum mechanics were complete, entangled particles would need to communicate instantaneously, violating relativity's cosmic speed limit, the speed of light. To Einstein, this meant the theory had to be flawed, missing hidden variables that would restore locality and determinism. But decades later, experiments proved the universe had other plans. In the 1960s, physicist John Bell formulated a mathematical test to settle the debate. His theorem showed that if hidden variables existed, entangled particles would correlate in a specific, limited way. Yet when scientists like Elaine Aspect ran the experiments in the 1980s, the results were unequivocal. Particles matched each other's states with a precision no hidden variable theory could explain. The implication: either the particles were communicating faster than light, breaking relativity, or their properties weren't fixed until measured, a notion even more radical. Modern labs have since confirmed entanglement across staggering distances. Chinese satellites have beamed entangled photons over 1,200 kilometers, with their linked states surviving the journey. Researchers have even entangled macroscopic objects like tiny drums visible to the naked eye, proving this quantum weirdness isn't confined to the subatomic world. The mechanism remains a mystery. Some theories propose particles exist in a higher dimensional space where distance is an illusion. Others suggest the universe is fundamentally non-local, with every particle subtly connected in a vast, invisible web. Yet entanglement isn't just a philosophical puzzle, it's the backbone of emerging technologies. Quantum computers harness entangled qubits to perform calculations impossible for classical machines, while quantum encryption uses entanglement to create unhackable codes. The particles themselves seem to follow rules written outside our spacetime, playing a game we're only beginning to decipher. Every time we test entanglement, the universe hands us the same answer: reality at its core is far stranger than we dreamed. Imagine waking up one morning and discovering that the air around you isn't empty, it's an invisible syrup clinging to your body, slowing your movements, giving you weight. That's essentially what the Higgs field does for every particle in the universe. Unlike gravity or electromagnetism, this isn't a force that pushes or pulls. It's more like an ocean we're all swimming through, an energy field stretching across every inch of space, and its interaction with particles is what gives them mass. Without it, the universe would be a chaotic soup of weightless particles zipping around at the speed of light, never clumping together to form atoms, stars, or you. The idea emerged in the 1960s when physicists Peter Higgs and others proposed a radical solution to a glaring problem. Why do some particles have mass while others, like photons, don't? Their answer was a cosmic molasses, a field that particles drag through, creating resistance we perceive as mass. The heavier the particle, the stronger its interaction with the field. Electrons barely sink into it, which is why they're lightweight, top quarks. They're practically drowning in it, making them hundreds of thousands of times heavier. For decades, the Higgs field remained theoretical until July 4, 2012, when scientists at CERN Large Hadron Collider announced they'd found its telltale signature, the Higgs boson. This elusive particle isn't the field itself, but rather a ripple in it, like a splash in that cosmic syrup. To detect it, they smashed protons together at nearly light speed, recreating conditions a trillionth of a second after the Big Bang. Trillions of collisions later, they spotted a tiny bump in the data, a particle decaying in exactly the way the Higgs should. But here's the twist: the Higgs field doesn't just give particles mass, it shapes the universe's very structure. If the field was slightly weaker, electrons would be too light to form stable atoms, too strong, and stars would burn out in a cosmic blink. Some theories even suggest the field might not be stable, that a random quantum event could one day shift its value, rewriting the laws of physics in an instant. The discovery closed one chapter in physics but opened a labyrinth of new questions. Why is the Higgs boson so lightweight compared to predictions? Does it hint at undiscovered particles or hidden dimensions? And could the field's delicate balance be a clue to something even grander? a multiverse where other regions of space have entirely different rules. The Higgs isn't just a particle. It's the universe's silent choreographer, dictating how everything from quarks to galaxies moves, and without it, none of us would be here to wonder why. Deep underground, in mines and beneath mountains, scientists chase shadows particles so elusive they pass through a light year of lead without a single collision. These are neutrinos, the universe's most aloof inhabitants, streaming from stars, supernova, and even your own body by the billions every second. For decades, they baffled physicists by vanishing en route from the sun, as if the cosmos were playing a shell game with its own building blocks. The solution, a quantum magic trick called neutrino oscillations, where these shape-shifters change identities mid-flight, rewriting the rules of particle physics in real time. The mystery began in the 1960s when detectors on Earth kept counting fewer solar neutrinos than theories predicted. Either our understanding of the sun's nuclear furnace was catastrophically wrong, or something strange was happening to the neutrinos during their 8-minute journey to Earth. The answer emerged decades later. Neutrinos weren't disappearing, they were disguising themselves. The sun produces only electron neutrinos, one of 3 known flavors. But by the time they reach Earth, some have morphed into muon or tau neutrinos, slipping past detectors tuned to their original form. This metamorphosis is only possible if neutrinos have mass, a revelation that sent shockwaves through physics. The Standard Model, our most precise theory of particles, had long assumed they were weightless, but oscillations proved otherwise. These phantoms must have at least a whisper of mass to flip between flavors. The mechanism hinges on quantum superposition. Each neutrino exists as a blend of all 3 states, and as it travels, the phases of these states shift, altering the probability of which flavor emerges when measured. Picture a spinning coin that simultaneously heads, tails, and edge, only collapsing into one outcome when caught. The implications stretch far beyond solar puzzles. Neutrino oscillations hint at physics beyond the Standard Model, possibly involving extra dimensions or undiscovered particles. They've also solved cosmic riddles, like why the universe isn't drowning in antimatter. Reactions in the early cosmos might have favored matter over antimatter through neutrino interactions, tilting the balance toward galaxies, planets, and life. Today, experiments like Super Kamioka and an ice cube watch for neutrinos from supernova, black holes, and distant galaxies, using their oscillations as cosmic fingerprints. Each detection peels back another layer of the universe's most enigmatic particles, ghosts that refuse to obey the rules we wrote for them. Their silent dance reminds us, even the smallest things hold secrets that can upend our grandest theories. Somewhere out in the cosmos, a bubble could be expanding at the speed of light, rewriting reality as it goes, not with fire or chaos, but with silence. This isn't science fiction. It's vacuum decay, a hypothetical doomsday scenario where the very fabric of space could drop into a lower energy state, erasing the laws of physics as we know them. The universe as we understand it might exist in a precarious condition, a false vacuum, like a marble resting at the top of a hill, stable for now but capable of rolling into a deeper valley with a single nudge. The idea stems from quantum field theory. Empty space isn't truly empty. It hums with potential energy, a property baked into the fields that govern particles and forces. Our universe's current vacuum state might not be the lowest possible energy level, it's just a local minimum, a temporary resting place. If a quantum fluctuation or high-energy event, perhaps in a distant galaxy, nudged a patch of space into the true vacuum, it would create a bubble where the fundamental constants change. Inside, electrons might dissolve, atoms unravel, and gravity vanish. The bubble's walls would spread at light speed, erasing physics in their wake. By the time we saw it coming, it would already be here. The stakes couldn't be higher. A vacuum decay event wouldn't just destroy Earth, it would rewrite the cosmos. Stars, planets, even the bonds holding molecules together could cease to exist in the new vacuum's rules. The eerie part, we'd never see it coming. The bubble could form anywhere, anytime, triggered by particle collisions in some distant lab or a random quantum jump in deep space. Nobel laureate Steven Weinberg once compared our universe to a frozen lake on a spring day. It seems solid, but beneath the surface the ice is thinning. Yet there's a twist. Vacuum decay might be impossible. Some theories suggest the Higgs field, which gives particles mass, could already be in the true vacuum. Others argue that quantum tunneling into a lower state is so improbable that the universe will die of heat death long before it happens. But the uncertainty lingers like a cosmic riddle. If we're living in a false vacuum, every high-energy physics experiment, every particle collider technically rolls the dice. The odds are astronomically low, but the consequences are infinite. What's haunting isn't just the idea of annihilation, but the realization that the universe's laws might be temporary. The constants we rely on, the speed of light, the strength of gravity, could be accidents of our local vacuum, as fleeting as a soap bubble in the wind. Vacuum decay forces us to confront an unsettling truth. Reality might not be as solid as it seems, and somewhere out there in the endless dark, the universe might already be rewriting its own rules. Black holes aren't just cosmic vacuum cleaners, they're the universe's most confounding paradox machines. At their edges, the laws of physics wage war, and one battle has raged for decades: the black hole information paradox. It all started when Stephen Hawking made a startling prediction in the 1970s. Black holes, he said, aren't completely black. They emit radiation, slowly leaking energy until they evaporate entirely. But here's the catch: if a black hole vanishes, what happens to all the information it swallowed? Stars, planets, even the unfortunate astronaut who fell in, does their data simply disappear? Quantum mechanics says no. Every particle state should be preserved like a cosmic ledger that can never be erased. Yet Hawking's math suggested black holes might be the ultimate shredders, violating quantum unitarity, the principle that information must never be lost. For years, physicists wrestled with this contradiction. Some, like Leonard Susskind, argued that information isn't destroyed. It's scrambled and encoded in the radiation itself, like burning a book but preserving its words in the smoke. This led to the holographic principle, a mind-bending idea that all the information inside a black hole is actually smeared across its event horizon in 2 dimensions, like a cosmic DVD. Later, we could theoretically play it back from the Hawking radiation, reconstructing the lost data. Then came an even wilder twist: the firewall paradox. If information escapes, quantum mechanics demands that the event horizon becomes a searing wall of energy, incinerating anything crossing it. But that contradicts Einstein's relativity, which insists falling into a black hole should feel like nothing at all until it's too late. So which is it? A serene descent into darkness or an abrupt cosmic bonfire? The debate remains unresolved, but recent breakthroughs in quantum gravity, like the ER=EPR conjecture, suggest wormholes might secretly link particles inside and outside the black hole, preserving information through quantum entanglement. What's at stake isn't just academic. If black holes can permanently delete information, our entire understanding of reality might need rewriting. The universe, it seems, has locked its secrets inside these gravitational vaults, and physicists are still hunting for the key. Time isn't the steady, unchanging river we perceive. It's more like a stretchy fabric, warped and twisted by gravity and motion in ways that defy common sense. Imagine 2 identical clocks, one on Earth's surface, the other aboard a satellite orbiting high above. Leave them running for a year, and you'll find the satellite clock has gained about 45 millionths of a second over its earthbound twin. That tiny difference isn't a glitch. It's proof that time itself flows differently depending on where you are and how fast you're moving. This phenomenon, called time dilation, isn't just theoretical, it's baked into the tech we use every day. GPS satellites have to account for relativistic effects, adjusting their onboard clocks to stay synchronized with Earth. Without these corrections, your navigation app would misplace you by nearly 10 kilometers a day, turning road trips into chaos. The deeper explanation lies in Einstein's theory of relativity, which shattered Newton's idea of absolute time. Special relativity showed that the faster you move through space, the slower you move through time, like a cosmic trade-off where speed steals seconds. Picture a spaceship racing past Earth at near light speed. To an observer on the ground, the ship's clocks would crawl, its crew moving in slow motion. But to the astronauts inside, time feels normal. It's the rest of the universe that seems sped up. This isn't an illusion, it's how space-time works. Then comes general relativity, which adds gravity to the mix. The stronger the gravitational pull, the more time slows down. Near a black hole like Interstellar's Gargantua, where gravity is crushing, time drags so severely that 1 hour on a planet orbiting it could equal 7 years back on Earth. The film's depiction wasn't Hollywood exaggeration, it was rooted in real physics. Einstein's equations reveal why. Time dilation stems from spacetime's curvature, the way massive objects like stars and black holes dent the cosmic fabric. The closer you are to the dent, the steeper the slope time must climb, making seconds stretch. The math can look intimidating, but the core idea is simple. Time and space are woven together, and anything that bends one affects the other. For GPS satellites, the interplay is delicate. Their high speed tries to slow their clock's special relativity, while Earth's weaker gravity at altitude tries to speed them up, general relativity. The net effect still leaves them ticking faster than ground clocks, hence the need for micro-adjustments. But the real mind-bender, time dilation, isn't symmetrical. If twins separate, one staying on Earth, the other traveling near light speed, the traveler returns younger than their sibling. This twin paradox isn't a thought experiment, it's been confirmed with atomic clocks on airplanes. The universe doesn't just have a single clock ticking uniformly. Every object, from a hummingbird to a galaxy, carries its own personal time, shaped by its motion and the gravity it feels. Time dilation forces us to abandon the notion of now as universal. What's happening right now on a distant star could be centuries in our past or future, depending on how space-time bends between us. The implications stretch beyond satellites and sci-fi. Time dilation shapes the cosmos itself. Near the Big Bang, when the universe was unimaginably dense, time would have flowed infinitely slowly from our perspective. A single second then could encapsulate billions of years now. Even today, supermassive black holes act as cosmic time machines, their extreme gravity stretching seconds into eons for anyone brave enough to approach. Yet here's the beautiful paradox. While relativity lets time bend, it forbids time travel to the past. The universe, it seems, is full of temporal flexibility, but never free of its own rules. Every ticking clock, from your wristwatch to the oldest star, whispers the same truth: time is anything but absolute. Magnetism is a force we all know. Your refrigerator door stays shut thanks to it. Compass needles point north because of it. But here's the twist. Every magnet we've ever encountered, from the tiny one holding up your grocery list to the colossal magnetic fields weaving through galaxies, has two poles. A north and a south. Always break a magnet in half, and you don't isolate the poles, you just get two new magnets, each with its own pair. This symmetry is so fundamental it's written into Maxwell's equations, the bedrock of electromagnetism. But what if nature has a secret? What if particles exist that carry just a single magnetic charge, a north without a south, or vice versa? These hypothetical entities are called magnetic monopoles, and their existence would rewrite physics as we know it. The idea isn't new. Back in 1931, physicist Paul Dirac showed mathematically that monopoles could explain why electric charge comes in discrete, unbreakable units, why electrons all have the exact same charge. His equations revealed a stunning link. If even one monopole exists in the universe, it would force electric charge to be quantized. It's as if magnetism and electricity share a hidden handshake, a cosmic rulebook we've only glimpsed. But Dirac's monopoles were more of a theoretical curiosity until grand unified theories came along. These ambitious frameworks aim to unite electromagnetism with the strong and weak nuclear forces, suggesting that in the unimaginable heat of the early universe, monopoles might have formed as defects in spacetime itself, like cracks in freezing ice. Here's where it gets cosmic. Some theories propose that as the universe expanded and cooled, its fundamental forces froze out unevenly, creating tangled loops of energy called cosmic strings, and monopoles could be the knots where these strings fray. If true, these particles would be unimaginably dense, perhaps even primordial black holes in disguise, carrying magnetic charges trillions of times stronger than anything in today's universe. The kicker, they'd also be relics of a time when all forces were one, making them living fossils from the first moments after the Big Bang. So why haven't we found them? The hunt has been relentless. Scientists have scoured lunar rocks, ancient mica crystals, and even the debris of particle collisions for traces of monopoles. Experiments like MOEDL at the Large Hadron Collider are designed to catch them, while detectors buried deep underground listen for the telltale ion trails monopoles would leave as they zip through matter. Some theories suggest they're just too massive to produce in modern accelerators, or so rare that only a handful drift through our galaxy. Others argue they might have catalyzed proton decay in the early universe, wiping themselves out and nearly taking matter with them. Yet the search persists because monopoles aren't just about magnetism. Finding one would be like uncovering a Rosetta Stone for physics, revealing clues about unification, the birth of the cosmos, and even the nature of spacetime itself. They're more than missing puzzle pieces, they're potential keys to a deeper layer of reality, hiding in plain sight. Whether lurking in the void or trapped inside neutron stars, monopoles remind us the universe might still be holding its most radical secrets close. Hidden behind the thick veil of stars and dust in our own Milky Way lies one of the universe's most baffling gravitational riddles, an immense, invisible force dragging entire galaxies toward it at unfathomable speeds. Astronomers call it the Great Attractor, a cosmic anomaly so powerful it bends the motion of hundreds of thousands of galaxies, including our own, as if space itself were a river flowing toward a hidden waterfall. This story begins in the 1970s when scientists mapping the universe's large-scale structure noticed something peculiar. The Milky Way, along with the entire local group of galaxies, wasn't just drifting aimlessly, it was racing toward a specific point in the constellation Centaurus at over 2 million kilometers per hour. But when they looked in that direction, they found nothing massive enough to explain the pull. The Great Attractor's elusiveness comes from its location. It sits directly behind the zone of avoidance, a region obscured by the dense plane of our galaxy, where dust and stars block our view like a cosmic blindfold. What little we've glimpsed through the haze suggests a mind-bending concentration of mass. The Norma cluster, a rich gathering of galaxies near the suspected center, hinted at part of the answer, but its gravity alone couldn't account for the staggering pull. The real breakthrough came when astronomers realized the Great Attractor might just be the foothill of something even larger. The Laniakea supercluster, a filamentary web of galaxies spanning 500 million light-years, with our Milky Way clinging to its outer fringes like a speck on a spider's thread. In this context, the Great Attractor isn't a single object but the gravitational heart of Laniakea, the point where the supercluster's immense mass balances the cosmic scales. Yet even this might not tell the whole story. Some theories propose that dark matter, the universe's invisible scaffolding, could be clumped here in unprecedented densities, weaving a gravitational trap for galaxies. Others speculate about more exotic possibilities, a primordial flaw in space-time from the universe's birth, or even the lingering influence of an ancient collision with another supercluster. The truth is, we're still peering through a keyhole, trying to decode an enigma that reshapes our understanding of cosmic motion. Here's what makes it eerie. If the Great Attractor's pull continues unabated, distant civilizations billions of years from now might witness our galaxy and all its neighbors vanish into this gravitational abyss, swallowed by forces we can't yet see. It's a humbling reminder, even as we map the cosmos, the universe keeps its greatest mysteries just out of sight, lurking behind the stars. What if the universe has particles that laugh at the speed limit of light? Enter tachyons, hypothetical entities that permanently travel faster than light, flipping causality on its head. While these speedsters are a staple of sci-fi, popping up in everything from time travel plots to warp drives, their theoretical roots dig deep into quantum field theory, where they emerge not as fantasy but as mathematical possibilities that challenge our grasp of reality. The idea traces back to 1962, when physicist Gerald Feinberg coined the term tachyon from the Greek word for swift. Unlike ordinary particles which slow down as they gain energy, tachyons would behave bizarrely. The more energy you take away from them, the faster they'd go. Picture a car that accelerates when you ease off the gas, except this car's minimum speed isn't zero, but the speed of light itself. They'd never slow down below that threshold, existing in a realm where time and space trade places. Here's where it gets mind-bending. According to relativity, if tachyons existed, they'd violate causality, the principle that cause must precede effect. A tachyon emitted from Earth toward a distant star could, from another observer's perspective, arrive before it was even sent, effectively traveling backward in time. This isn't just a quirk of perception. The math suggests such particles could create closed time-like curves, enabling paradoxes like the infamous grandfather paradox, where someone could theoretically prevent their own existence. Quantum field theory doesn't rule them out entirely. Tachyons appear in certain equations as unstable modes, often signaling a system's transition to a lower energy state. In condensed matter physics, similar behavior crops up in superfluids or superconductors, where collective excitations can mimic tachyon-like properties without breaking physical laws. Some theories even propose that the Higgs field, before settling into its current state, might have briefly acted like a tachyon during the universe's infancy, a fleeting instability that helped shape the cosmos. Yet the biggest hurdle remains. No experiment has ever detected a tachyon. Efforts to spot them range from hunting for Cherenkov radiation in space, a faster-than-light particle's version of a sonic boom, to scouring high-energy collisions for anomalies. The null results suggest that if tachyons exist, they're either fantastically rare or cleverly hidden. Some physicists argue they're mere mathematical artifacts, while others speculate they might be confined to extra dimensions or only interact with our universe gravitationally. Sci-fi, of course, adores them. From Star Trek's subspace communications to Doctor Who's timey-wimey technobabble, tachyons are the go-to-handwave for breaking physics when the plot demands it. But the real fascination lies in what they reveal about our universe's boundaries. Tachyons force us to ask, are the speed of light and causality truly unbreakable, or are they just the limits of our current understanding? Whether they are out there or not, these phantom particles remind us that the universe's rulebook might still have chapters we've yet to read. Even the emptiest corners of space are anything but empty. If you could peer into the quantum realm, you'd find a seething ocean of energy bubbling beneath the surface of reality, a phenomenon called zero-point energy. According to quantum mechanics, there's no such thing as perfect stillness. Every cubic centimeter of the vacuum hums with fleeting particles and antiparticles popping in and out of existence, a chaotic dance known as quantum foam. This isn't just theoretical, it's measurable. In the late 1940s, physicists Hendrik Casimir and Dirk Polder predicted that these quantum fluctuations could produce a real physical force. Place two uncharged metal plates incredibly close together in a vacuum, and the sheer abundance of virtual particles outside them should push the plates inward. The result, a detectable pressure now called the Casimir effect. Scientists first observed it in the lab in 1997, proving that so-called empty space is bursting with untapped energy. The implications are staggering. The vacuum's zero-point energy density is calculated to be around 10 to the power of 113 joules per cubic meter, enough in theory to boil Earth's oceans instantly. Yet here's the cosmic irony. While this energy is everywhere, it's virtually impossible to extract. Think of it like standing in the middle of a hurricane with a cup trying to catch the wind. The energy is immense, but it's locked in a state of perfect balance, canceling itself out at every moment. Any attempt to siphon it would require manipulating space-time itself, something far beyond our current technology. Some speculate that advanced civilizations might tap into zero-point energy as the ultimate power source. Warp drives, interstellar travel, even time manipulation could hinge on mastering this quantum sea. But the mysteries go deeper. Zero-point energy might hold clues to dark energy, the force accelerating the universe's expansion. Some theories suggest that vacuum fluctuations could be driving cosmic acceleration, except the numbers don't add up. The predicted energy is 10 to the power of 120 times larger than what we observe. This colossal mismatch, called the cosmological constant problem, is one of physics' greatest unsolved puzzles. Are our calculations wrong? Is there a hidden mechanism suppressing most of this energy? Or is the universe fine-tuned in ways we don't yet understand? Experiments continue to probe these questions. Quantum physicists manipulate microscale devices to measure Casimir forces with atom-thin materials, while theorists explore exotic ideas like negative energy densities and warp bubbles. Visualizing quantum foam remains a challenge. It's a realm where spacetime itself churns like a stormy sea at scales 1 trillion times smaller than an atom. Some simulations depict it as a fractal labyrinth of twisting, splitting, and reconnecting threads, a chaotic foundation upon which reality is built. For now, zero-point energy remains a tantalizing paradox, an infinite reservoir of power just beyond our grasp, woven into the very fabric of nothingness. It's a reminder that the universe's greatest secrets don't always hide in distant galaxies. Sometimes they're right in front of us, humming silently in the space between atoms. Wormholes, those fantastical cosmic shortcuts woven into the plot of every sci-fi epic, aren't just Hollywood magic. They're a genuine prediction of Einstein's general relativity, stitched into the fabric of spacetime itself. Picture space as a vast sheet of paper folded so two distant points touch. A wormhole, also called an Einstein-Rosen bridge, would be a tunnel piercing through that fold, turning a billion light-year journey into a stroll across the cosmic backyard. But here's the catch: these space-time tunnels are notoriously unstable. The moment one forms, gravity would slam it shut like a bear trap, crushing anything inside before even a photon could slip through. Kip Thorne, the physicist behind Interstellar's scientifically grounded wormhole, revealed the loophole: exotic matter. Not just any matter, this hypothetical substance would need negative energy density, warping spacetime in ways that defy everyday physics. Unlike normal matter, which always attracts via gravity, exotic matter would repel, propping the wormhole's throat open like cosmic scaffolding. Quantum mechanics offers a glimmer of hope here. The Casimir effect, where vacuum fluctuations create regions of negative pressure, hints that such exotic physics might not be impossible, just wildly beyond our current reach. Sci-fi often treats wormholes as subway stations, fixed, stable, and conveniently placed. Reality is far messier. even if exotic matter exists, a traversable wormhole would require engineering on a scale that bends the mind. Thorne calculated that stabilizing a 1-meter-wide wormhole might demand the equivalent mass energy of Jupiter converted into exotic material. And then there's the feedback problem. Any particle entering would create destabilizing energy surges, potentially collapsing the tunnel mid-transit. Yet the math keeps physicists intrigued. Wormholes aren't just shortcuts, they're tangled with quantum entanglement and black hole paradoxes. Some theories suggest entangled particles might be connected by microscopic wormholes, a concept dubbed ER=EPR. Others ponder whether wormholes could link universes in a multiverse, or serve as time machines with one mouth accelerated to near light speed to create a time differential. The catch: time travel through wormholes risks unleashing catastrophic paradoxes, from reality-splitting inconsistencies to infinite energy feedback loops. For now, wormholes remain cosmic what-ifs, but they're more than just equations. They're testaments to how wildly creative the universe's rules can be, where space-time isn't just curved but foldable, and where the line between science fiction and science fact blurs into tantalizing possibility. The universe might not be what it seems, a three-dimensional space full of stars, planets, and galaxies. What if everything we see, touch, and experience is nothing more than an illusion, a two-dimensional surface projecting a holographic mirage of depth? This mind-bending idea isn't science fiction. It's called the holographic principle, a theory that redefines reality at its core. It all started with black holes, those cosmic paradoxes that swallow information whole. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, its measure of disorder, is directly tied to the surface area of its event horizon, not the volume inside. Later, Stephen Hawking confirmed that when black holes evaporate, they release radiation but seemingly destroy the information they consumed. This sparked a crisis. Quantum mechanics insists information can never be lost. So where does it go? The answer emerged from string theory. In 1993, physicist Gerard T. Hooft proposed a radical solution. What if all the information inside a black hole isn't actually inside? Instead, it's smeared like a cosmic tattoo across the event horizon's two-dimensional surface, perfectly preserved. Leonard Susskind and others expanded this idea into the holographic principle, suggesting the entire universe might work the same way. Just as a credit card hologram encodes a 3D image on a flat surface, reality as we know it could be a projection from a lower dimensional boundary at the edge of existence. The math behind this comes from the AD/S/CFT correspondence, a groundbreaking concept in string theory. It shows that a higher dimensional space like our universe can be mathematically equivalent to a theory operating on its lower dimensional boundary, like a movie screen encoding every detail of a 3D world. Imagine every particle, every force, even your thoughts, being pixels on an unimaginably vast cosmic canvas. But here's the real kicker: we might never notice the difference. The holographic principle doesn't mean the universe feels flat to us. It means the richness of our 3D experience emerges from deeper, encoded information, just as temperature emerges from the motion of atoms. Experiments at Fermilab's holometer have even searched for telltale pixelation in spacetime itself, hunting for quantum fuzziness that might betray the illusion. If true, the implications are staggering. Reality wouldn't just be stranger than we imagined, it would be fundamentally different. Space and time, matter and energy might all be secondary phenomena, shadows cast by something far simpler. The universe wouldn't have depth in the way we think, just layers of information like a cosmic sleight of hand. So the next time you look up at the stars, ask yourself, are they really out there, or are we all just lines of code on the universe's ultimate screen? The answer might rewrite existence itself. Among the countless candidates vying to solve the dark matter mystery, one stands out not for its heft, but for its almost ghostly lightness: the action. These hypothetical particles weren't dreamed up to explain missing mass in the cosmos. Instead, they emerged from a puzzle buried deep inside the atom, where the laws of quantum chromodynamics, the rules governing quarks and the strong nuclear force, seemed to be breaking their own symmetry. In the late 1970s, physicists Roberto Pexi and Helen Quinn proposed a radical fix, a new field pervading the universe that would restore balance. The side effect, ripples in that field would manifest as particles' actions, named after a laundry detergent because they promised to clean up the problem. Unlike their hulking dark matter cousins, WIMP, actions would be staggeringly light, perhaps 1 trillion times lighter than an electron. But here's the twist: they'd make up for their featherweight nature by existing in unimaginable numbers, flooding the cosmos like an invisible quantum fog. Their properties are bizarre. Actions wouldn't interact with light except in the presence of intense magnetic fields, where they might occasionally transform into photons, offering a faint but detectable signal. That quirk is the key to hunting them. Enter ADMX, the Action Dark Matter Experiment. Nestled deep underground at the University of Washington, this ultra-sensitive detector is essentially a high-tech radio receiver tuned to the universe's quietest station. Inside a powerful magnet, ADMX scans microwave frequencies, listening for the telltale click of an action converting into a photon. The challenge: the signal would be so weak that it's drowned out by the thermal noise of the detector itself. To counter this, ADMX chills its sensors to near absolute zero and employs quantum amplifiers so precise they can detect single photons. The stakes couldn't be higher. If actions exist, they wouldn't just solve the dark matter riddle. They'd bridge particle physics and cosmology, tying together mysteries from the quantum realm to the cosmic web. Some theories even suggest actions might explain another puzzle: why the neutron's electric field is perfectly round despite being made of charged quarks. Others speculate they could influence the evolution of stars, subtly altering how heat escapes stellar cores. Yet the search is like looking for a whisper in a hurricane. Actions could occupy any frequency across a vast range, and scanning them all is a painstaking process. Recent upgrades to ADMX, including quantum squeezing techniques, have dramatically boosted its sensitivity, bringing us closer than ever to either catching an action or ruling them out entirely. What makes this hunt so captivating isn't just the science. It's the audacity of the idea that something so tiny, so ephemeral, could hold the universe together. If actions are real, they'd be a testament to how deeply interconnected the cosmos truly is, where the solution to a subatomic imbalance might also be the hidden glue binding galaxies. The search continues, with every quiet beep in the day a potential revolution in waiting. Imagine every star you've ever seen is just one grain of sand on an endless beach, and that beach itself is one of countless others stretching beyond the horizon of existence. This is the essence of the multiverse, a concept so vast it redefines reality itself. Not just one universe, but many, perhaps infinite, each with its own laws, its own history, even its own version of you. Scientists don't just entertain this idea as wild speculation. They've categorized multiverses into distinct levels, each more mind-bending than the last. Let's start with level I, the simplest and hardest to dismiss. If space is truly infinite, as cosmic inflation suggests, then somewhere beyond our observable horizon, the same quantum fluctuations that seeded our galaxies must repeat. Given enough space, every possible arrangement of matter recurs endlessly. Somewhere out there, an identical Earth orbits an identical Sun, with doppelgangers living your life down to the smallest detail, while other versions veer wildly off script. The kicker: we'll never see them. Light from those regions hasn't had time to reach us in the universe's 13.8 billion-year lifespan. This isn't sci-fi. It's a direct consequence of infinity plus quantum randomness. Then comes level Roman 2, where things get surreal. Remember cosmic inflation, that explosive stretching of spacetime after the Big Bang. Some theories suggest it never truly stopped, that our universe is just one bubble in a frothing sea of inflating space, each bubble a separate universe with its own physics. Picture a pot of boiling water, where each steam bubble nucleates with different properties, some with stronger gravity, others with extra dimensions, perhaps even some where time runs backward. String theory's landscape problem feeds into this. The math allows for 10 to the power of 500 possible vacuum states, each a potential universe. The constants we take for granted, the strength of gravity, the mass of an electron, might just be lottery numbers drawn in our particular cosmic bubble. But level Roman 3 is where the mind truly reels. This is the quantum multiverse, born from the many worlds interpretation. Every time a quantum particle faces a choice, like whether to spin up or down, the universe doesn't pick one outcome. It splits, branching into parallel timelines where all possibilities play out. Missed a bus this morning, somewhere a version of you caught it, lost a coin toss. Another you is celebrating heads. Unlike level I, these branches share the same space-time but decohere like radio channels tuned to different frequencies. The eerie part, this isn't metaphysics, it's a legitimate solution to quantum mechanics measurement problem, removing the need for observers to collapse wave functions. Critics, of course, raise the obvious question: if we can't observe other universes, is this even science? Some theorists argue yes, that certain multiverse models leave subtle fingerprints. A level Roman 2 bubble collision might imprint a cold spot on the cosmic microwave background, like a bruise from a cosmic car crash. Level Roman 3 could betray itself through quantum interference if branches briefly reconnect. Even string theory's landscape, once deemed untestable, might be probed by studying the distribution of fundamental constants across possible universes. If ours sits in a statistically likely neighborhood, it hints at a vaster ensemble. Yet the debate rages: is the multiverse a profound insight or a philosophical cop-out, a way to dodge explaining why our universe seems fine-tuned for life? For now, it remains a dazzling possibility, a reminder that reality might be grander, stranger, and more interconnected than we ever dared dream. Whether cosmic foam, quantum branches, or infinite repeats, the multiverse challenges us to rethink not just where we are, but what we even means in a cosmos without end. At the heart of our sun, where temperatures soar to 15 million degrees and pressures crush atoms together with unimaginable force, a miracle occurs millions of times every second, but it shouldn't be possible. Protons, positively charged and fiercely repulsive to one another, somehow fuse into helium, powering the star that gives us life. Classical physics says this can't happen. The electromagnetic barrier between protons is like a mountain taller than Everest, and the particles in the sun's core simply don't have enough energy to climb it. Yet they do by cheating. They tunnel right through. This is quantum tunneling, one of the strangest and most consequential tricks in nature's playbook. On the subatomic scale, particles aren't just tiny balls, they're fuzzy clouds of probability, existing in multiple places at once until measured. When a proton approaches another, there's a small but real chance it'll suddenly appear on the other side of the electromagnetic barrier, as if teleporting. It's not magic, it's Heisenberg's uncertainty principle in action. The more precisely you pin down a particle's position, the less certain its momentum becomes, and this inherent fuzziness lets it borrow energy briefly to hop through walls. The sun isn't an exception, it's proof that tunneling isn't just theoretical. Without it, stars wouldn't shine and the universe would be cold and dark. But tunneling doesn't just light up the cosmos, it powers your daily life. Every modern device, from smartphones to satellites, relies on transistors, the tiny switches at the heart of microchips. Early transistors worked by brute force, shoving electrons across barriers with sheer voltage. Today's nanoscale chips exploit tunneling deliberately. Electrons flit through insulating layers thinner than a strand of DNA, enabling the lightning-fast calculations in your pocket. Too much tunneling can cause leaks, frying circuits, but engineers walk that tightrope, crafting barriers just thick enough to control the flow without stifling speed. The implications get even wilder when you scale up. Some theories suggest tunneling could explain cosmic mysteries like vacuum decay, where a quantum jump in the Higgs field rewrites physics. Others propose it might play a role in DNA mutations, as protons tunnel between genetic strands, altering life's code. Even the Big Bang might owe something to tunneling, a quantum fluctuation that bypassed the universe's initial energy barrier, birthing spacetime from nothing. Yet tunneling remains eerily counterintuitive. In labs, particles routinely escape sealed containers, slipping through walls like ghosts. Cold fusion, the controversial dream of clean energy, hinges on whether tunneling can be harnessed to fuse atoms at room temperature. While mainstream science remains skeptical, the mere possibility highlights tunneling's disruptive potential. From the heart of stars to the chips in your hand, quantum tunneling defies the rules we thought governed reality. It's a reminder that on the smallest scales, the universe plays by its own logic, one where walls aren't obstacles but invitations. The next time you feel stuck, remember, even protons have a way through. The night sky is a vast ocean of stars, each one a potential sun to another Earth. With billions of galaxies, each harboring billions of planets, the numbers scream that we shouldn't be alone. And yet radio silence, no signals, no artifacts, no visitors. This crushing quiet is the Fermi paradox, the jarring disconnect between the universe's staggering potential for life and the eerie absence of any proof it exists beyond Earth. The paradox takes its name from physicist Enrico Fermi, who, over a casual lunch in 1950, posed a devastatingly simple question: where is everybody? The Drake equation, crafted by astronomer Frank Drake in 1961, lays out the variables that should determine how many communicative civilizations exist. Start with the rate of star formation, then factor in planets per star, the fraction where life could arise, the subset where intelligence evolves, and so on. Plug in optimistic numbers and the galaxy should be buzzing with activity, but our telescopes hear nothing. This silence suggests something's wrong, either with our assumptions or with the universe itself. The leading explanation, great filters. These are cosmic or evolutionary hurdles so severe they prevent life from reaching interstellar stages. Some filters might lie in our past, rare, fluke events like the moon-forming collision that gave Earth a stable climate or the emergence of DNA itself. If these steps are improbably lucky, we might truly be alone. But the more terrifying possibility is that the filter awaits us in the future. Perhaps all advanced civilizations inevitably destroy themselves through nuclear war, runaway AI, or ecological collapse. The silence wouldn't be proof of absence, but a graveyard warning. Other theories offer less grim answers. The zoo hypothesis suggests advanced societies deliberately avoid contact, observing us like a cosmic nature preserve until we reach maturity. There's the dark forest model, where civilizations stay hidden, fearing that any broadcast invites annihilation from predatory aliens. Or maybe we're searching the wrong way, scanning for radio waves when others have moved to neutrino comms or quantum entanglement. The truth might be even stranger. Life could be common, but intelligent life absurdly rare. Dinosaurs ruled Earth for 160 million years without inventing radio. Or perhaps we're early. The universe is only 13.8 billion years old, and most habitable planets lie in the far future. The Fermi paradox isn't just about aliens. It holds up a mirror to humanity. Every day we don't find life, the more urgent the question becomes: are we the universe's first, last, or only shot at knowing itself? The answer, whatever it is, changes everything. Consider a thought so unsettling it upends our understanding of existence. What if you, right now, aren't the product of billions of years of evolution, but a fleeting accident? A random fluctuation in the void, a momentary spark of self-awareness conjured from chaos. This is the Boltzmann brain paradox, a cosmic horror story written in the language of thermodynamics. The idea traces back to Ludwig Boltzmann, the 19th century physicist who linked entropy, the universe's march toward disorder, to the arrow of time. In an eternal cosmos, he reasoned, even the most improbable events must occur eventually. Given enough time, atoms in a perfect vacuum could spontaneously arrange themselves into a functioning brain, complete with false memories of a past that never happened. Not just once, but countless times. Statistically, these phantom minds should outnumber real, biologically evolved beings like us. So why does the universe feel so consistent? The paradox cuts to the heart of cosmology. If the universe began in a low entropy state, as the Big Bang suggests, why haven't random, high entropy Boltzmann brains dominated reality by now? Some theories propose our universe isn't eternal, but part of a multiverse where low entropy pockets like ours are rare oases. Others suggest consciousness itself might act as a filter, making real observers more probable than statistical flukes. But the most chilling implication, we could be Boltzmann brains destined to dissolve into the void the moment we question our own existence. The debate isn't just philosophical. It exposes gaps in our understanding of time, entropy, and quantum mechanics. If self-aware entities can blink into being from nothingness, what does that say about the nature of reality? Are the stars above, the ground beneath your feet, just figments of a disembodied mind's dying hallucination? The cosmos offers no easy answers, only the uneasy silence of infinite possibilities. In the vast ocean of stars, one flickering anomaly has astronomers and alien hunters alike scratching their heads. 8,462,852, better known as Tabby's star. Nestled in the constellation Cygnus, this seemingly ordinary star made headlines in 2015 when data from NASA's Kepler Space Telescope revealed its bizarre behavior. Unlike most stars, which dip in brightness predictably when planets orbit past, Tabby's star dims erratically, sometimes by a staggering 22%, as if something enormous and irregular is passing in front of it. The dips don't follow any pattern, lasting days or weeks before vanishing as mysteriously as they appeared. At first, scientists assumed a swarm of comets might be to blame, a family of icy debris orbiting the star in a tight, chaotic dance. But the numbers didn't add up. To block that much light, you'd need millions of comets, an implausibly dense cloud with no known natural precedent. Then came the bombshell suggestion from astronomer Jason Wright. What if we're seeing the shadows of alien megastructures, specifically a Dyson swarm, hypothetical constructs built by an advanced civilization to harness their star's energy, like a vast array of solar panels orbiting the sun? The idea wasn't pulled from thin air. Freeman Dyson himself proposed in the 1960s that sufficiently advanced civilizations might dismantle planets to build such megastructures, capturing nearly all their star's light. Tabby's star's erratic dimming fit the profile eerily well. The real twist, this cosmic detective story began not with a team of PhDs but with citizen scientists. Kepler's raw data was public, and volunteers with the Planet Hunters Project, ordinary people combing through light curves, first flagged the star's odd behavior. Professional astronomers initially dismissed it as noise, but the amateurs kept pressing. Their tenacity paid off, proving that in an era of big data, curious minds outside academia can still crack the universe's biggest puzzles. Yet the mystery only deepens. Follow-up studies have ruled out some natural explanations, like interstellar dust or a recent planetary collision, but none fit all the data perfectly. The star's long-term dimming, it's faded by about 14% over the past century, adds another layer of intrigue. Some suggest it's slowly consuming a planet, while others propose internal stellar processes we don't yet understand. The alien megastructure theory, while tantalizing, remains a last resort, a classic case of when you hear hoofbeats, think horses, not zebras. but in science, sometimes the zebras turn out to be unicorns. For now, Tabby's star keeps its secrets flickering cryptically against the void. Whether the answer is comets, undiscovered physics, or something beyond our imagination, one thing's certain: the universe still has plenty of surprises up its sleeve. And sometimes, all it takes is a keen-eyed amateur to remind us just how strange and wondrous the cosmos can be. The cosmic microwave background, that faint afterglow of the Big Bang, should be the ultimate testament to cosmic democracy, a perfectly uniform canvas with no preferred direction, no special place. That's the Copernican principle in action. Earth isn't the center of the universe, and neither is any other point, or so we thought. Enter the axis of evil, a spine-chilling pattern etched into the CMB that defies everything we assumed about cosmic fairness. When the Planck satellite mapped the CMB with microscopic precision, scientists expected randomness, a scattering of hot and cold spots like a child's finger painting. Instead, they found something that made their blood run cold. The fluctuations weren't chaotic. They aligned along a specific axis, as if the universe had quietly drawn a line through space and whispered, "This way is special." The odds of this happening by chance, less than 1 in 1,000. It's like rolling a die 100 times and getting only 6s technically possible, but screaming that something's deeply wrong with our assumptions. This axis isn't just a statistical hiccup. It points eerily toward the ecliptic plane where our solar system's planets orbit. Even stranger, it aligns with the mysterious dark flow, the unexplained motion of galaxy clusters racing toward a distant attractor. The implications are staggering. If the universe has a preferred direction, it means our laws of physics built on isotropy, the idea that space looks the same in all directions, might need rewriting. The Copernican principle, the bedrock of modern cosmology, could be on shaky ground. Some theorists scramble for conventional explanations. Maybe it's residual noise from our own galaxy's magnetic field, or an artifact of how we process CMB data. But the more we correct for these factors, the more the axis of evil lingers like a stubborn ghost. Others entertain radical possibilities: a pre-Big Bang structure imprinted on spacetime, a collision with another universe during inflation, or even evidence that we're inside a cosmic defect, a wrinkle in the fabric of reality itself. The Planck data didn't just raise questions, it exposed how much we still don't understand about the universe's architecture. If the axis of evil is real, it's not just an anomaly, it's a crack in the foundation of cosmology, a signpost pointing toward uncharted physics. And until we decipher its meaning, the universe remains a puzzle with pieces we didn't even know were missing. Phantom energy isn't just another form of dark energy, it's a cosmic doomsday scenario with teeth. While ordinary dark energy accelerates the universe's expansion gently, like a steady breeze pushing galaxies apart, phantom energy does something far more violent. It grows stronger over time, amplifying its grip until not even atoms, molecules, or the fabric of spacetime itself can withstand its force, the end result. A big rip, where every star, planet, and particle in existence is torn asunder in a final, catastrophic moment. Picture the universe not just fading into cold darkness, but actively unraveling first galaxies, then solar systems, then planets, and finally the very electrons orbiting atomic nuclei. It's not merely an ending, it's annihilation on a scale that makes black holes seem quaint. The concept emerged when cosmologists realized dark energy's equation of state. The ratio of its pressure to energy density might not be constant. If this value dips below -1, dark energy transforms into phantom energy, acquiring a terrifying property: the ability to intensify as space expands. Unlike ordinary dark energy, which dilutes as the universe grows, phantom energy feeds on itself, becoming exponentially more dominant with each passing eon. The math behind this is chilling. Current models suggest that if phantom energy exists, the Big Rip could occur in as little as 22 billion years, a blink of an eye on cosmic timescales. But here's the twist: the universe might already be offering us clues. Supernova surveys, the same observations that first revealed dark energy's existence, act as cosmic speedometers, measuring how the expansion rate has changed over billions of years. Data from missions like the Dark Energy Survey and the upcoming Vera-Rubin Observatory scrutinize these distant stellar explosions with unprecedented precision, hunting for any deviation from the standard dark energy model. So far, the results lean against phantom energy. Supernova's brightness patterns align better with a constant dark energy equation of state. Yet the margin of error leaves room for doubt. Phantom energy could still lurk at the edge of detectable limits, its full fury waiting to manifest. What makes this hunt so urgent is the sheer stakes involved. If phantom energy is real, it wouldn't just rewrite cosmology textbooks, it would impose an expiration date on reality itself. Unlike the slow heat death of the universe, where stars fade and matter decays over incomprehensible eons, the Big Rip would be a definitive, almost cinematic finale. Structures would be shredded hierarchically, galaxy clusters first, then individual galaxies, stars ripped from their orbits, planets reduced to dust, and finally atoms themselves dissolving into quantum foam. No force, no bond, no law of physics would remain untouched, yet nature seems to resist this apocalyptic vision. The universe's large-scale structure, the delicate web of galaxies and voids, shows no signs of the extreme distortion phantom energy would cause. Even dark energy's apparent constancy over billions of years suggests a stability that phantom energy lacks. Some theorists argue that phantom energy violates fundamental energy conditions in quantum field theory, making it physically implausible. Others counter that our understanding of dark energy is still in its infancy, and exotic states like phantom energy might emerge under conditions we haven't yet imagined. The debate isn't purely academic. If phantom energy exists, its early effects might already be detectable. Astronomers scan for subtle changes in the clustering of galaxies or anomalies in the cosmic microwave background that could hint at growing repulsive forces. The absence of such signals tightens the noose around phantom energy's neck, but doesn't quite eliminate it. For now, the universe keeps its ultimate fate close to the vest, leaving us suspended between the eerie silence of deep space and the looming specter of a reality that might one day tear itself apart at the seams. High above Earth, drifting silently in the frozen darkness of space, an object has fueled conspiracy theories for decades: the so-called Black Knight satellite. Tales swirl of an alien probe, perhaps thousands of years old, silently observing humanity from orbit. Some claim it's sent radio signals since before the space age, or that its origins trace back to ancient astronaut encounters. But the truth, as so often happens, is far stranger than fiction, because the Black Knight isn't one thing, but a tangled web of misidentified debris, Cold War secrecy, and our own hunger for cosmic mysteries. The myth's origins are murky. Some point to radio signals allegedly detected by Nikola Tesla in 1899. Odd pulses he speculated might be extraterrestrial in origin. Decades later, in the 1950s, newspapers reported anomalous echoes picked up by early radar systems, sparking fears of Soviet surveillance satellites. Then came the grainy photos, a dark, irregular shape glimpsed during early NASA missions, seized upon as proof of an artificial object not of human making. The legend crescendoed when a 1998 Space Shuttle Endeavour mission captured images of a peculiar, tumbling object during an orbital debris survey. To believers, this was the smoking gun, an ancient artifact adrift in our skies. Reality, however, is less cinematic. The Black Knight phenomenon is a classic case of pareidolia, our tendency to see patterns in randomness. The satellite is likely a collage of unrelated events. Those anomalous radar echoes, they were probably ionospheric disturbances, natural plasma fluctuations that bounce radio waves unpredictably. The famous NASA photos analysis reveals they almost certainly show a thermal blanket lost during an EVA, its crumpled surface catching sunlight at eerie angles. As for the Endeavour debris, it matched the dimensions and material of a panel from the International Space Station, torn loose during assembly. Space is littered with human-made flotsam, discarded rocket stages, dead satellites, even a lost glove, all capable of looking sinister when viewed through the lens of conspiracy. Yet the persistence of the Black Knight myth reveals something profound about human psychology. We crave mystery, especially in the vast unknown of space. The idea that we're being watched, that some intelligence might have beaten us to orbit, taps into deep-seated fears and fascinations. It's no coincidence that these stories peak during times of technological anxiety, the Cold War space race, the dawn of the digital age. The Black Knight endures because it's a blank screen onto which we project our hopes and unease about humanity's place in the cosmos. But here's the twist: while the Black Knight itself might be myth, the broader question it raises isn't silly. Scientists actively hunt for extraterrestrial artifacts through initiatives like the Galileo Project, scanning the solar system for anomalous objects. In 2017, Oumuamua, the first known interstellar visitor, sparked legitimate debate about its unusual acceleration, though natural explanations like outgassing eventually prevailed. The line between fringe theory and serious science is thinner than we think. Maybe the real lesson of the Black Knight isn't about aliens at all, but about how easily the universe can fool us and how much we still long to be surprised. On August 15, 1977, a radio telescope at Ohio State University's Big Ear Observatory picked up something that would become one of the most tantalizing mysteries in the search for extraterrestrial intelligence. A signal so extraordinary that astronomer Jerry Amon circled it on the printout and scrawled, "Wow." In the margin, this 72-second burst of radio waves originating from the direction of the constellation Sagittarius blazed at a frequency of 1420 MHz, a sacred number in astronomy known as the hydrogen line. Why that frequency? Hydrogen is the simplest and most abundant element in the universe, the raw material of stars and galaxies. Any civilization with even basic knowledge of physics would recognize 1420 MHz as the resonant frequency of neutral hydrogen, the point where it emits and absorbs energy most naturally. It's like a cosmic lighthouse, a universal channel any technologically advanced species might tune into. The wow signal wasn't just loud, it was surgically precise, narrowband, and unmodulated, characteristics consistent with an artificial origin. Natural phenomena like pulsars or quasars typically broadcast across a range of frequencies, but this was a laser-like beacon screaming from the void. Then came the real puzzle. Despite decades of follow-up observations, the signal never repeated, not once. Astronomers scanned the same patch of sky with far more sensitive instruments, like the SETI Institute's Allen Telescope Array, but found only silence. The signal's ephemeral nature fuels endless debate. Was it a one-time transmission, perhaps an alien beacon sweeping past Earth like a searchlight? Could it have been a fragment of a longer message we only caught the tail end of? Or more mundanely, was it a reflected signal from human technology, like a satellite or military experiment, bouncing off space debris in a freak alignment? The last possibility has gained traction in recent years. Some researchers suggest the signal might have originated from a passing comet's hydrogen cloud, though the frequencies don't quite match. Others point to secret Cold War-era probes, though no declassified records corroborate this. What's undeniable is the wow signal's cultural impact. It's become a symbol of both the promise and frustration of SETI. A fleeting whisper that, for one brief moment, made the universe feel alive with possibility. But here's the haunting thought: if it was artificial, the implications are staggering. The signal's strength suggests an emitter far more powerful than anything we've built, something capable of focusing energy across interstellar distances with pinpoint accuracy. A civilization advanced enough to broadcast at that scale might not need to repeat itself. They could be signaling thousands of targets in sequence, patiently waiting for a reply we haven't sent. Or perhaps the message wasn't meant for us at all, and we simply eavesdropped on someone else's conversation. The WOW signal endures because it embodies the essence of science at the edge of the unknown, a single data point too perfect to ignore, too elusive to confirm. It's the cosmic equivalent of hearing your name whispered in a crowd, only to turn and find no one there. Whether it was a hello from the stars or just the universe playing tricks, one thing's certain: sometimes the most profound mysteries aren't about what we find, but what we're left longing to hear again. In 1998, NASA scientists noticed something strange happening to the Pioneer 10 and 11 probes, two intrepid spacecraft that had already made history by venturing farther into the solar system than any human-made object before them. The probes, launched in the early 1970s, were now drifting toward the outer edges of our cosmic neighborhood, but their trajectories weren't matching predictions. Though hurtling through the void with no obvious obstacles in their path, they were slowing down ever so slightly, as if an unseen hand were gently tugging them backward. This tiny but persistent deceleration became known as the Pioneer anomaly, and for over a decade it baffled physicists, sparking theories that ran from the mundane to the spectacular. At first, the numbers seemed to defy explanation. The probes were experiencing a constant, unmodeled acceleration toward the Sun, just under 9 nanometers per second squared. To put that in perspective, it's about 10 billion times weaker than Earth's gravity, barely enough to affect a speck of dust. But over years of travel, even this minuscule drag added up, pushing the probes hundreds of kilometers off course. The discrepancy was too small to write off as an instrument error, yet too consistent to ignore. Some researchers speculated wildly: was there an unknown force at play in the outer solar system? Could it be a flaw in our understanding of gravity itself? Maybe even a hint of dark matter's invisible grip. Then came the breakthrough one that reminded scientists how often the universe's greatest puzzles have the simplest explanations. After years of painstaking analysis, a team discovered the culprit wasn't some exotic physics or hidden cosmic force. It was heat. The probe's plutonium-powered radioisotope thermoelectric generators were emitting tiny amounts of thermal radiation, and because of Pioneer's unique design, that radiation wasn't perfectly symmetrical. The probe's dish-shaped antennas acted like reflectors, bouncing infrared photons preferentially in one direction back toward the Sun. Over decades, this faint but relentless photon recoil acted like a microscopic brake, gradually altering the spacecraft's path. The resolution might sound anticlimactic, but it's a lesson in scientific humility. Sometimes the answers we seek are hiding in plain sight, obscured only by our assumptions. The Pioneer anomaly didn't rewrite physics or reveal a new law of nature, but it did teach us how even the tiniest overlooked details can ripple across vast distances. Every measurement, every calculation has to account for the universe's full complexity, down to the quiet push of a single photon. And yet, there's something poetic about this invisible nudge. The same heat that kept Pioneer's instruments running, that powered humanity's first forays into the outer solar system, also became the force that ever so gently pulled it back. A cosmic irony written in thermal whispers: the universe, it seems, loves its quiet symmetries even when they slip past us for decades. In October 2017, humanity got its first confirmed visitor from another star system, a mysterious object hurtling past the Sun at nearly 200,000 miles per hour. Astronomers named it Oumuamua, Hawaiian for scout, but this cosmic interloper left far more questions than answers in its wake. Unlike any asteroid or comet we've seen before, Its shape, motion, and sheer strangeness sparked a firestorm of debate that still rages today. The first clue something was off came from its trajectory. Oumuamua didn't orbit the Sun in a neat elliptical path like solar system objects. It barreled in at a steep angle, looped around our star, and shot back out into interstellar space like a slingshot pellet. This extreme hyperbolic orbit screamed alien origin, but the real shock came when telescopes measured its brightness. Over hours, the object's luminosity swung wildly by a factor of 10, suggesting it wasn't a roundish body but something long and thin, tumbling end over end. Picture a cosmic cigar stretching perhaps 600 feet long but only 60 wide, a shape never before seen in nature. Astronomers scrambled to classify it. Was it a comet? Traditional comets sprout glowing tails when sunlight vaporizes their icy surfaces, but Oumuamua showed no such activity until it did something even weirder. As it raced away from the Sun, it sped up slightly as if pushed by an unseen force. Comets often accelerate like this due to outgassing, where evaporating ice acts like a natural rocket thruster. But no tail, no icy haze, nothing visible explained the boost. Some proposed it might be an ultra-dry comet, one that vented invisible gas. Others argued it was more like an asteroid, perhaps shorn from a shattered world light years away. Enter Avi Loeb, Harvard's controversial astrophysicist, who dropped a bombshell hypothesis: Oumuamua might be artificial. His light sail theory suggested the object's unusual acceleration could be explained by solar radiation pressure, the same force that powers experimental spacecraft like Earth's own light sail project. If Oumuamua was a thin, flat sheet, perhaps a defunct solar sail from an alien civilization, it would catch the photons streaming from the Sun like wind in a sail, nudging it forward without needing gas or engines. The shape, the acceleration, even the way it tumbled, all fit Loeb's model eerily well. The scientific pushback was immediate. Critics pointed out that while Oumuamua was strange, invoking aliens violated Occam's razor, the principle that simpler explanations should prevail until proven wrong. They proposed exotic natural alternatives. Maybe it was a fractal like dust bunny of primordial material, or a chunk of hydrogen ice that vaporized without visible residue. Some even speculated it could be a shard from a shredded planet, its unusual properties shaped by extreme tidal forces near a distant star's gravity well. Yet the debate revealed how unprepared we are for interstellar guests. By the time telescopes spotted Oumuamua, it was already speeding away, leaving us just weeks to study it. Future observatories like the Vera Rubin telescope aim to catch the next visitor earlier, giving us time to probe its secrets. Whether Oumuamua was a comet, an asteroid, or something else entirely, its brief flyby taught us one thing: the universe is full of surprises, and some of them might be knocking on our door. Earth isn't just a rock with life clinging to it, it's a living, breathing entity in its own right, maintaining perfect balance against all odds. This radical idea, known as the Gaia hypothesis, emerged from the mind of chemist James Lovelock in the 1970s, proposing that our planet operates like a colossal self-regulating organism. Picture the atmosphere, oceans, and biosphere not as separate systems, but as interconnected gears in a vast machine, constantly adjusting to keep conditions just right for life. Oxygen levels, temperature, even ocean salinity, all fine-tuned with precision that defies random chance. Lovelock's eureka, a moment came while working for NASA, designing instruments to detect life on Mars. He realized Earth's atmosphere is wildly out of chemical equilibrium, brimming with reactive gases like oxygen and methane that should have neutralized each other long ago. The only explanation, life itself, was actively maintaining this instability. From this insight, Gaia was born not as a conscious deity, but as a metaphor for the planet's uncanny ability to self-correct. When carbon dioxide rises, plants thrive and absorb more. When temperatures climb, phytoplankton bloom, releasing cloud-seeding compounds that reflect sunlight. It's as if the biosphere has a built-in thermostat. To prove his theory wasn't mystical nonsense, Lovelock created Daisyworld, a simplified computer model featuring a planet covered in black and white daisies. Black daisies absorb heat, warming the world. White ones reflect it, cooling things down. As the model's sun grows hotter, the daisy populations automatically shift. More white flowers appear to counteract the heat, stabilizing temperatures within a habitable range. No intelligence required, just feedback loops. This elegant simulation showed how life could unconsciously regulate a planet's climate, silencing critics who dismissed Gaia as pseudoscience. Yet controversy persists. Evolutionary biologists like Richard Dawkins argue Gaia contradicts natural selection. Why would species altruistically cooperate to stabilize the planet? Others contend Earth's history is littered with catastrophes like snowball Earth episodes and mass extinctions, hardly evidence of careful balance. Lovelock's response: Gaia isn't infallible. The system can tip into new stable states, some hostile to life as we know it. Industrial pollution and climate change might be such a tipping point, pushing Gaia toward a feverish equilibrium where humans are no longer welcome. Modern science has softened the debate. While few accept Gaia as literal biology, Earth system science now embraces its core premise that life and environment are deeply entwined in feedback cycles. The nitrogen cycle, the carbon cycle, even the way forests generate their own rain, all echo Lovelock's vision. Even his harshest critics admit Earth behaves as if it's self-regulating, even if there's no grand plan. Gaia's true legacy might be philosophical. It forces us to see Earth not as a stage for life, but as life itself, a single dynamic entity where bacteria and hurricanes are equal players. In an age of climate crisis, that perspective isn't just poetic. It's a survival manual reminding us that tampering with one thread risks unraveling the whole tapestry. The planet will endure. The question is whether we'll still have a seat at the table. What if everything you've ever experienced, the taste of coffee, the warmth of sunlight, even the stars above, was just an elaborate simulation? This isn't the plot of a sci-fi movie. It's the simulation argument, a serious philosophical proposition that our reality might be nothing more than lines of code in some advanced civilization's computer. The idea gained traction in 2003 when philosopher Nick Bostrom laid out a chilling trilemma. At least one of these statements must be true. Either nearly all civilizations go extinct before reaching technological maturity. No advanced civilizations care to run ancestor simulations, or we're almost certainly living in one right now. Bostrom's logic is deceptively simple. If future civilizations develop computing power vast enough to simulate conscious minds, and if even a fraction of them choose to run simulations of their ancestors, the number of simulated beings would dwarf the number of biological ones. Statistically, the odds you're one of the real originals are vanishingly small. Think of it like this: if 1% of humans today played hyper-realistic historical video games, and each game contained billions of self-aware characters, the simulated population would outnumber real humans billions to one. You'd have to be staggeringly lucky to be among the flesh and blood few. But where's the evidence? Some theorists point to quantum mechanics as potential glitches in the matrix. Take wave function collapse, the way particles seem to exist in multiple states until observed. Could this be a computational optimization, like a video game rendering details only when a player looks? Even spacetime's pixelated nature, hinted at by Planck-length discreteness, mirrors how graphics engines prevent infinite detail. And then there's quantum entanglements, faster than light linkage, which Einstein called spooky. In a simulation, this might just be two variables sharing memory addresses, no physics breaking required. Critics counter that these phenomena have natural explanations rooted in quantum field theory. But the simulation hypothesis isn't about proof, it's about probabilities. If creating conscious simulations is possible, and if post-human societies have any motive to run them, the math suggests we're more likely avatars than ancestors. The counterintuitive twist: this might not be dystopian. Our simulators could be benevolent researchers, artists, or even descendants ensuring humanity's legacy survives cosmic extinction. The argument forces a profound question: does it matter? If the simulation is indistinguishable from reality, then pain, joy, and meaning remain just as vivid. But the possibility lingers, a whisper behind the equations, that reality might be far stranger than we ever dared dream. Whether glitch or gospel, the simulation hypothesis doesn't just challenge what we are. It redefines what real could even mean. From the ghostly whispers of dark matter to the cosmic stretching of phantom energy, these 30 unseen forces aren't just quirks of physics, they're the invisible threads weaving reality's tapestry. Each one, from quantum entanglement's spooky connections to the Great Attractor's gravitational pull, reveals a universe far stranger and more intricate than we ever imagined. They shape galaxies, dictate time's flow, and even hint at realities beyond our own. Think of it this way: every time you look up at the night sky, you're not just seeing stars. You're witnessing the aftermath of inflation's explosive birth, the dance of neutrinos born in stellar furnaces, and the silent hum of zero-point energy bubbling beneath the void. These forces are the architects of existence, the quiet puppeteers behind everything from the atoms in your body to the fate of the cosmos itself. Carl Sagan once reminded us of our tiny place in this grand scheme with his iconic pale blue dot, a single pixel in the vast cosmic dark. But here's the beautiful paradox: while we're small, our curiosity is boundless. Every mystery we've unraveled, from the Higgs field to black hole paradoxes, started with a simple question. And for every force we've explored today, there are countless more waiting to be discovered. So stay curious, wonder about the actions that might lurk in the dark, the wormholes that could hide in spacetime's folds, or the simulation glitches that might betray reality's code. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and that's what makes the journey so exhilarating. Now, over to you. Which of these cosmic forces left you awestruck? Was it the eerie fine-tuning of the cosmological constant, or the brain-bending holographic principle? Drop your favorite in the comments, because the greatest discoveries begin with shared curiosity. After all, we're all stardust trying to understand itself.